All right, so now that we've identified how we can assess past climate change, let's investigate how and why Earth's climate has changed in the past. All right, so in this video, we will connect the timing and changes to Earth's orbit with the timing and changes of glacial cycles. These orbital changes turn out to be a really big influence on when the climate has changed in the past. We'll also appreciate that these changes in solar energy don't do it themselves. They're amplified by the climate system, and we'll talk about how that works. We'll also compare the major climate regimes over the past 65 million years of Earth history. All right, but first let's try to get a sense of scale here for the magnitude of Earth history that we're going to be considering. It can be really difficult to translate our human lives that we live out in days and hours into the really unimaginably long history of Earth. But here goes. So the Earth is 4.56 billion years old, which is essentially the same thing as saying it's 4,560 million years old. So this is the age that we derive when considering how much of the uranium on Earth has turned into lead through radioactive decay. And so what I did here is I went on a map. You can see UH over here. And I looked for somewhere that was around 4.56 kilometers away, or 2.83 miles. And here, that's around Diamond Head. So if you're not in Oahu, I'd encourage you to find your own landmarks that fit this distance. You can use Google to do this. But here at UH, there's this one crosswalk on Dole Street. The campus center is sort of back this way. But you can see Diamond Head through the trees here. So Diamond Head here is around 4.56 kilometers away. And if each kilometer is a billion years in this kind of scaling exercise, then each meter is a million years. So basically, by the time you've taken 2 steps across this crosswalk, you've covered basically a million years of geologic time equivalents. All right, so if you start where I was when I took this picture, and you just start sort of walking towards Diamond Head, you'll notice right here, maybe it's a bit hard to see, but there's this sort of arch that you go under when you're going to the parking structure. So that is essentially, 180 feet, so 65 meters, more or less. That's the amount of time that's passed since the dinosaurs went extinct. That's 65 million years. So from here over to here. Some other important cutoffs. So if you take 1 step, you're covering at least 500,000 years. That's the time that modern, anatomically accurate humans have been in existence, that 1 step. So we know such a very small amount of Earth history. And so, yeah, and as long as this semester seems, if you think about the last 6 months, you're basically covering only a distance of half of a micron, which is basically the size of a bacterial cell, the width. So, yeah, it's really kind of humbling to think in these kind of massive geological scales. But keep that in mind when we're talking about climate change over hundreds of thousands and millions of years, that even those are, just kind of scratching the surface at the length of Earth history. So this is the record of Delta 18O that we saw in the last video. And so this is basically maybe, one long step. It covers this whole amount of time here, with humans sort of coming up, in this area 200, 400,000 years ago. So humans as a whole have seen, a few of these glacial periods where you have high Delta 18O because the temperatures are cold, and a few of these interglacial periods like that we're living in today. And that's really about it. That's sort of what the Earth as humans know it has been. But you'll notice that these cycles keep repeating back and forth, and that there's these little sort of bumps along the way. So what's causing this kind of timing? What's causing these shifts? They appear pretty regular, right? All right, well, let's come back to human timescales for a second. So what causes our environment to change? What causes things to become colder and warmer? And this is kind of obvious, but it's worth, it's worth going into. So if you think about day and night, one of the major rhythms of our life, right? It's light out in the daytime, it's dark out at night. When the sun is shining, things heat up. And when the sun sets, things cool down. So that sort of sets this rhythm up, down, if you think of this axis of irradiance or insolation, or how much sunlight that we're getting or how much energy from the sun we're getting. So up, down, up, down, up, down. You can keep going and just go through these oscillations for every day that there ever was. But there's an easier way to sort of express this oscillations, and that's by thinking about frequencies. So here, instead of time, the units are basically 1 divided by time. And then you would have this peak in sunlight intensity that would sort of correspond to these 24-hour days. So this is the time scale of day and night, basically. So if you go to slightly longer frequencies here, you'll find the second peak. This is the sort of 12-month seasonal cycle. So here, I'm just going to hide myself. And so now you can see, you can represent this single peak here as these 365-day cycles that keep going for every year of Earth history. So we can think about how these add together. So if you consider, a warm summer night, right? You're at the low point of this cycle, but the high point of this cycle here versus a winter day. You can imagine that one of these factors is going to win out. That might actually vary depending on where you are. But these are sort of ways that we can express sort of the tempo of climate change. All right, and just as a fresh reminder, the reason we have seasons in the first place is because the Earth has a tilt. So the axis that Earth rotates on here is not the same axis that it orbits on, which is sort of vertical up here. So Earth is sort of moving here and around in this orbit, but it's tilted. And so in one part of this orbit, in the summer solstice for the northern hemisphere, you have the sort of northern hemisphere receiving all the sun rays that when things flip the other way and in winter, there's sort of an equal and opposite loss of sunlight, and that's why things are cold in the winter. And then you have this sort of equal and opposite increase in sunlight for the southern hemisphere, because the summer solstice is at different points in the year for different hemispheres. So the seasons are not because the Earth is closer to the sun in summer or farther away in winter. It's because of this tilt of the Earth. So in addition to the daily and seasonal frequencies of change, there are changes in Earth's orbit that happen over much longer timescales. These are called the Milankovitch cycles, after the astrophysicist who calculated them. And basically what he did was he observed how Earth's orbit changed from year to year in these really, really minute ways. But he was able to observe this and basically calculate how that would change going forward and backward in time. So here are the major components of the Milankovitch cycles. So the first one is the eccentricity of Earth's orbit. So most of us imagine Earth sort of moving around the sun in this kind of circle here, but that's actually not quite right. It's really more of an elliptical orbit. And the degree of this ellipsis, the eccentricity of it, changes over timescales of around 100,000 years or so. So at one point, on the cycle, Earth's orbit is nearly circular. So every position around the sun as you go through the seasons is at a similar distance from the sun, and so receives the baseline solar energy, and just about the tilt that creates seasons. But 50,000 years go by, you're at this other cycle where Earth has a more eccentric orbit. And so what effect does that have? Well, we said in the circular orbit we have more even seasons here, but in the eccentric orbit, you could have your summer solstice out over here. So even though you're facing towards the sun, now you're further away from the sun. So your summers aren't going to be as hot. That's maybe only for the northern hemisphere. In the southern hemisphere, that means your winters are going to be even more extreme. And then if you go to the other side of this, you might expect a more mild, sort of a warming effect for both seasons, for both hemispheres. So if this is your summer solstice here, then you would expect more sunlight coming in your summer solstice, so hotter summers. And then meantime, this is the winter solstice for the southern hemisphere. They're going to have a milder winter. So that's how eccentricity sort of affects the sunlight, coming into Earth. Let's move on. The second type of these Milankovitch cycles is obliquity. So this is basically describing the tilt of the Earth, like how tilted Earth's axis is. And this is a 40,000-year cycle. So every 20,000 years, you're in the sort of opposite phase. So at its peak here, you'll get more tilted Earth. So summers will be hotter, winters will be colder, because the poles are sort of more inclined towards the sun in summer and more away from the sun in winter. But at this trough, then the Earth is more vertical, and so the seasonal contrast is weaker. And finally, there's precession. So this is the hardest one to grasp. The characteristic timescale for precession is around 20,000 years to go up, down, up, down. So it's a much faster one. It's actually not set at 20,000 years. There's orbits within precession. So It can vary from anywhere between 19 and 23,000 years. So to understand the effect of precession, it's easiest to think of like a spinning top. So imagine a top is sort of spinning around around its primary axis here, but over time, that sort of location of the stick on top of the top, that wobbles over time. And so right now, Earth's axis points basically straight towards the star Polaris, which is our North Star. But if you wait 13,000 years, Earth's axis will actually be pointing somewhere completely different. It'll be pointing towards Vega. And so this is sort of describing the sort of two extremes of this precession cycle, where this sort of axis continues to rotate. And so you can imagine, so here's how this might affect the seasons. I'm just going to hide myself. So yeah, so this is sort of tracing Earth's orbit sort of from the summer solstice to the autumn equinox, winter solstice, and around and around. And you can see here, this is Earth's astronomical orbit as it rotates around the sun. And it happens to line up now with the summer equinox being right here, where Earth's northern hemisphere is most exposed to the rays from the sun. But the effect of precession is to slowly sort of rotate Earth so it's pointing the opposite way. And so when we're pointing towards Vega in the year 15,014, this spot in our astronomical orbit will actually become our winter solstice. Yeah, this sort of changes the timing of the season with respect to Earth's sort of astronomical positioning and all of that. So we can add these modes of variability together, and we can see that in addition to the daily and seasonal sort of peaks in solar radiation frequency, there are these much longer time scales of precession at 22,000 years, obliquity at 42,000 years, and eccentricity at 100,000 years. So now let's imagine that you're living in the Arctic. This is sort of where these effects are sort of most extreme. But imagine you're living in the Arctic and summer's finally here, and there's barely enough sunlight integrated over the entire summer to melt last year's snow. So now let's imagine that a few years pass and the Earth enters a new obliquity cycle. So let's say your summers become even less warm because the Earth is slightly less tilted. So instead of completely melting all the snow that fell in winter, now in summer there's still some snow left. And so year after year this builds up. And this is how you would form ice sheets and how you could transition the Earth into a glacial state. Once you have lots of ice sheets, they start reflecting more sunlight back out to space. Earth starts to cool, and there's this runaway process that just needs a slight trigger of how much sunlight there was in summer. So this is kind of the amplification effect that leads to massive climate change. All right, so here's what this looks like when you add all of these kind of like wiggles together. So on this y-axis here is this term installations. It's pretty common in the paleoclimate world. It's basically how much solar energy was coming to Earth's surface at that point in time. And these are sort of values that you'd predict at 65 north, so up in the high Arctic where these kind of snow melting or not melting decisions are kind of most intense. And so you can see, looking at these, there are these sort of a lot of movement up and down, but you can see there's certain periods where you have these more extreme times here. So here you have an extreme low in solar insolation, then you go and end up back close to normal. You have another extreme low, extreme high here. You have this time where there's really not much variation overall. And then you have the biggest parts here, the most extreme highs and the most extreme lows here. This is the combination of eccentricity and precession and obliquity cycles all adding together in this case to make the warmest summer possible, and in this case to make the coldest summer possible. And so these are sort of ways that you can reach tipping points in the Earth system. And so like we said before, you can convert these oscillations into frequencies. And so here you see, here's the peak at 41,000 years. That's the major effect of obliquity. Obliquity is one of the biggest drivers here. But you can also see the role of precession here. These three peaks are actually part of the precession signal. So this is for this time before, this is basically the last million years. This is from 1 million years to 2 million years ago. You can see the same peaks emerge. It's the same path of Earth's orbit. There's a peak at obliquity at 41,000 years, and these precession peaks as well. All right, so now let's look at the Delta 18O record. So this is a slightly different version than what we've been looking at. It goes back through 2 million years. But you can see the same kind of ups and downs as before. This is our most recent Holocene here. The axis is actually flipped. So this is low values here, high values in the last glacial period, low values, high, low, high, low, etc. All throughout the past 2 million years. You can see these frequencies are still there. And so when you look at, when you plot these instead of a time series as a comparison of frequencies, you can see here that this 41,000 year band is really strong. So you can see that this effect of obliquity, this change in the tilt of the Earth, is basically traveling through the Earth system, ending up in calcium carbonate inside organism shells, and that's being buried at the bottom of the ocean in the tropics, basically. So I think this is kind of nuts. One of the really cool and mysterious things here is actually these things change over time. So you can see here over the last million years we have this really strong 100 kiloyear frequency, so that's 100,000 years. And you can see that by eye here. These are these big glacial cycles, really big swings in delta 18. These are really intense ice ages and more intense interglacials. But these are really a phenomenon only of the past million years or so. And if you remember the last plot where we had the most extreme insulation changes, that's often thought to be a driver for the shift from this prior age where you still had glacial cycles, you still had these up and downs. But you'll notice they're closer together and they're not as intense. They don't span the same amplitude. And here, when you do the frequency analysis of this 1 million to 2 million year block, what you'll find is, again, a big period at 41 kiloyears obliquity, but you don't see anything in 100,000 years. So there's been some change in the Earth system from this earlier time, 1 million to 2 million years ago, versus the last million years that now has changed the tempo of climate change. And to be honest, no one really knows why this happened. There's a lot of ideas about ice sheets reaching a certain point where they're basically too big to fail, and then you have these massive swings when ice sheets collapse. So, but this is a matter of active research and debate. But it's one of the more fascinating things. All right, but actually one of the sort of complicated aspects about these Milankovitch cycles and their role in climate change is that the changes in insolation are, although meaningful, they're relatively small. We're talking about something like a 10 to 20% change in the amount of sunlight that a given location will get in summer over thousands and thousands of years. And so, just that energy alone isn't enough to make the planet cold or hot, depending on the level of irradiance. So really, it's climate change on the global scale arises because these input signals are amplified by the climate system. And so the idea is that in order to for the Earth to make big change in its climate, switch from a glacial state to an interglacial state, or vice versa, you have to have all these amplifiers that kind of distort these input signals. So the input signals are the Milankovitch cycles. There are changes in how much sunlight you get in summer, how much you get in winter, when does summer really start, things like that. So these are precession, obliquity, and eccentricity, and these are sort of inputs into this climate system that has seasonal effects on biology. It has greenhouse gases that basically control how much of the incoming sunlight is retained in the Earth. There are things like ocean atmosphere system, right? This is basically how efficiently heat at the equator gets transferred, into the poles, and how much energy is sort of conveyed into the deep ocean. These things like this. These are these kind of amplifiers, or sometimes I like to think of like an auto tune, where you have a normal voice that has maybe some strange pitches into it, and then it gets put into this contraption basically. And then what comes out are something that's maybe a bit more extreme. It's amplified, set to the different pitches here, and even the time scale can kind of change because of this. So really, understanding these Milankovitch cycles alone aren't enough. This is just telling us when we might expect changes. Really, the hard part is understanding, how these gears actually interact with each other to create, a change from an interglacial here, where you have little ice in the Arctic, to this sort of massive expansion of ice sheets down here and then back. And so one of the really crazy parts here is you can see this in nature when you have the right conditions here. So this is a really famous area called Punta de Maiata in Sicily. These are carbonate sedimentary rocks, basically laid down from organisms like coccolithophores growing in the Mediterranean over the past basically 4 million years, forming sediments. Those sediments are compacted. When more sediments come back on them, they slowly compress into sedimentary rocks, and then they get uplifted through tectonics and put up on the land. So this is a segment for its 3.75 million years on the top. These are sort of younger sediments, 4.5 million years old on the bottom. And you can see just all these lines here, all these different strata. And actually, you can pick out some of these climate cycles here. So you can see here, these sort of thicker bands correspond to the 100 kiloyear cycles. So you can see them down here. And then you can actually see what we didn't really touch on, but these 400,000 year cycles as well. So, and you can actually go into different, finer resolution and see influences of precession in these sort of darker lines. So it's really kind of fascinating that, again, this is something that is just the amount of sunlight coming into to the Earth, and then here you see it manifested in, in the contents of this, what was on the seafloor and now is in the rocks. And actually, people, I think, go to the beach here and walk around here. So, yeah, this is the world around you. All right, so the last thing that we'll do in this video is sort of run through this kind of history of Earth's climate over the last 65 million years or so. We'll touch on this again in the next video where we talk about how this interacts with the carbon cycle, which is a major component of these kind of gears that lead to climate amplification. But yeah, so let's see, over here, this is 66, 67 million years ago. This is when the dinosaurs died, and this asteroid came in. And yeah, and this is sort of the temperature since that happened. So, so these are from seafloor records. These are from the Delta 18O proxy that have been corrected for this glacier size effect through independent records, and so you're isolating that temperature component. They're from 4Ms, and this is like a continuous sequence over 67 million years. So this is sort of a phenomenal record of Earth change, and this is ultimately helping us understand the consequences of ongoing warming. So let's spend a couple minutes on this. This is a really rich figure. There's a lot to unpack. It's color-coded here, so you can kind of see these are the hotter times here in red. These are the colder times. And then actually the period that we're just coming out of, the sort of ice ages, including interglacials, are really anomalously cold in terms of the past 66 million years ago. This is a unique climate based on anything that's come before. So the glacial cycles that we're all looking at, right, those were going 1 or 2 million years ago. There's your 1 or 2 million year tick marks right there. So that was the last figure. Humans have been around for something that's smaller than this pointer here. So yeah, kind of humbling again. And you can see here, if you can't see this here, print out the slides and take a look. These sort of up and down extreme, these are the magnitude of glacial cycles here that are compressed here. But you can see these are sort of similar orbital forcing that keeps going along here. But the size of these changes, these are being affected by changes in well, lots of things, changes in plate tectonics, changes in the carbon cycle, all these changes that basically affect how those gears, how that auto-tune system takes in these original inputs and creates climate noises on the other side. Okay, so let's head back in time. So these are the glacial periods, anomalously cold. Things actually jump up when you enter the Miocene, maybe 5 million years old and older to 15 million years. We're at areas that are around 2 degrees warmer than today, and then they jump up to areas that are around 4 degrees warmer than today. So, and then this is sort of the Miocene and Oligocene era that basically goes to around 33 million years ago. Before that, there's a big jump up, and things start to get really kind of warm. Global average temperatures, right? So individual locations will heat up a lot more than others. Some locations might be relatively buffered, but this is a huge change in temperature. And these rise to this sort of maximum period in the Eocene, and then stays hot sort of into the Cretaceous. So you have this period, this kind of warm house and hot house where Earth is really hot, followed by this, some people might call it cool house, and then this ice house where you actually have glaciers. We have these sort of massive glaciation events. All right, so you have this top section in gray that also kind of charts the sort of history of ice sheets on Earth. And you can see that when we were in this ice house period over the last maybe 2-3 million years old, that's sort of the duration of northern hemisphere ice sheets. So the ice sheet that's still there today on Greenland, ice sheets across Canada in certain times in Europe and Siberia. These are not a persistent feature of Earth's history. They're only a few million years old. There's some small ones on Greenland that probably persisted for a while longer, but nowhere near the size that we even have today. And you can see that once you enter into this bipolar ice sheet, things cool down a lot. So let's go back in time. In this Miocene and Oligocene period, basically, let's say 5 to 33 million years ago, you still have a big ice sheet around Antarctica. So you still have a lot of ice in the South Pole. And this is sort of a cool climate still. But now look over here, you crossed over at 33 million years ago. This Antarctic ice sheet kind of dwindles down to kind of a bare minimum here. And then the Earth is really hot here. Once it loses the Antarctic ice sheet, it kind of loses this kind of ice cube in the drink, so to speak. And here you can see that these are called hyperthermal events. So you see the climate is kind of chugging along, and then boom. Actually, I should go the opposite way. The climate is chugging along, and then boom, a big warm spike. And then you see these sort of poke up in other areas too, sort of frequently throughout here. These hyperthermal events are unusual, and they're not really seen basically 33 million years to today. They're only observed when you don't have this Antarctic ice sheet sort of keeping everything steady, keeping everything cool. All right, and the last thing to point out is what will our future conditions be? And these are highly uncertain because our ability to simulate the climate system is not as good as our ability to reconstruct it often. So there's a lot of uncertainty. Even if we know how much CO2 is going to go out in the future, we still have a good deal of uncertainty about what's going to happen there. But we also don't know how much carbon humans are going to emit in the future. So there are these two uncertainties cascading onto each other. And for here you have this one emission scenario called RCP 8.5 that has these three trajectories based on uncertainties and how climate will sort of evolve in the future. But this scenario is basically the business as usual scenario. So if we do nothing to stop emissions and sort of let them proceed as the market demands, then this is sort of the future that we might arrive at. And maybe we can bet on this more resilient climate here and only experience maybe 4 degrees of warming. That would put us somewhere in this Oligocene cool house scenario. But in an extreme case, we could head up all the way into this 8 to basically 12 degrees of warming, and that's something that we haven't seen on Earth basically since in the last 30 million years. These are this sort of hothouse where we're basically losing all the ice, and so imagine how much sea level rise that entails. And so even if that is our future, and hopefully it's not, it'll take a while for that to manifest. Things don't happen overnight. But you can also look at some of these other scenarios. This light blue sort of captures the range of this RCP 4.5, which is often considered to be a more manageable, achievable future outcome. And this is leaving us with, in the low case, maybe 2 degrees of warming or 1.5 degrees of warming. In the high case, something like 4 degrees or so, which again is maybe enough to have some serious loss in the Greenland ice sheet, but it's still kind of a lot better than this business as usual scenario. But again, just to emphasize, where are humans in this plot? They're only right here, right? Humans have only lived in this stretch here where you have these, royal blues to really dark blues. Everything else is unprecedented in human history. All right, so maybe that's a lot to mull over, but at least now we've gone through how we think climate change has happened in the past. Starting with these kind of orbital triggers where you have these kind of buildup and maxima of, obliquity signals and eccentricity signals and precession signals, leading to sort of either really warm summers in high latitude places where it can melt a lot of ice, or really kind of lackluster summers and colder winters where the ice sheets can really get cranking. But really, these changes in sunlight aren't enough. They have to be amplified by everything else in the climate Earth system, through ocean circulation, through atmospheric circulation, through greenhouse gases. All of these come together to then lead this, the result, which is a change in climate. And that's really what is being measured with proxies like Delta 18O and reconstructed into global temperatures like we just went through. So next time we will talk more about greenhouse gases and their role in this.